Okay, thanks very much. I'm Wouter Swierstra, and I'm here to tell you a little bit about a JFP paper that I wrote, Correct by Construction Conversion to Combinators. So I thought I'd start with a little bit of historical context. So if you go back 100 years to the birth of the lambda calculus, there's a spirit of logical minimalism where people were looking for foundations for mathematics that used kind of a minimal number of constructions. And you had people like Haskell Curry and Moses Schoenfinkel on the left here, and they were looking for languages without variable binding that were powerful enough to describe all of mathematics. And many people will have heard of Haskell Curry, but maybe fewer people will have heard of Moses Schoenfinkel. And he's quite a tragic figure. He was a Ukrainian Jew who moved to Göttingen to work with David Hilbert and work on the foundations of mathematics there. And he managed to publish 2 papers during his career, neither of which he wrote himself, but both were transcribed by his colleagues based on talks that he gave. And he moved to Moscow after his stay in Göttingen, and he died in poverty, and after his death, Wikipedia tells me that his neighbors burned all of his books and notes to stay warm. So on that happy note, let's continue the talk. Combinatory logic is the kind of simpler alternative to the lambda calculus that I wanted to say a little bit about. And yet it's capable of expressing the same computations. So what's this paper about? It's a translation from the simply typed lambda calculus to combinatory logic, and it's implemented in Agda. And what's nice about the translation, if you look at the function, you can see that it's going to preserve types. So I don't have to do any proofs about type preservation. And in fact, if you look at the type of the translation function, you know that it's correct. It's going to preserve the semantics of the input lambda term in the combinator that it generates. So this is why the title, it's a correct by construction conversion to combinators. So what is combinatory logic? It's a very simple language. It looks just like the lambda calculus. You have variables in application. The only difference is that rather than having a lambda binding, so it's a language without binding, you have 3 constants, s, k, and I. And so you don't have any beta reduction. Instead, you have 3 kind of simple rewrite rules, which mimic reduction, it turns out. And this has been used as a target language for compilers for functional languages. I think we'll hear about this in the David Turner Memorial this afternoon, and Leonard will be giving a talk on his micro HS compiler that is kind of based on this idea as well. So there's no lambdas and no variable binding, yet somehow the claim is that these 2 are equivalent. It seems quite magical. So before I can kind of get towards the equivalence, I'm going to decide how to model the source language, how to model the simply typed lambda calculus. And there's a standard way to do this in Agda that I can quickly kind of go through here. So the first thing is I have my type language. I have a base type iota, and I have function types. So I better kind of model this in Agda, and I call this the type universe U, where I have a base type iota, and I have a function type, which is this funny fat right arrow. So this is the syntax of types that I have to now kind of explain what these types actually mean in terms of Agda. So I have these little semantic brackets that I'll write around these types, basically saying that the funny function arrow maps to Agda's function space, and the base type iota maps to some type A. It could be natural numbers or Booleans or whatever you like. And now there's a fairly standard way to model the simply typed lambda calculus intrinsically typed in Agda. If you look at the 3 typing rules, they're very kind of regular. They're perfectly syntax directed. So instead of defining raw terms and then saying the well-typed terms are the raw terms for which I can prove that they're well-typed, I can fold the well-typedness proof into the definition of the syntax. So you can see, for example, if you look at the type of application, you take a function and an argument, return a result, and that's exactly what you have here. Something similar happens for lambdas, where if you a lambda produces a function, and in the body you have access to 1 more variable, and the variables are kind of represented using this intrinsically typed De Bruijn representation. If that's complicated, just think of numbers. And now the nice thing about this kind of representation is that you can define an evaluator. And the evaluator is 3 lines long. It doesn't need any auxiliary definitions, or few, but to handle environments. But it's very, very simple. And it's actually magical that it works at all, because it's mapping a kind of application constructor to application in Agda. And it's mapping the lambda constructor to Agda's lambda here. And to make this all go through, there's one extra ingredient, which is not so important for the talk, but I need to record a heterogeneous list of variables which has a value for every variable which is in scope. So this is a well-known example of a dependently typed program. So what about combinatory logic, right? I already showed you the syntax that I needed to model. So one thing I could do is I could take this syntax and write a little data type for terms in combinatory logic. So I could see I have variables and applications and 3 constants, sk and I. But now if I try to define a translation function, it doesn't tell me much about the types involved. So at this point, you can see the translation will take some term which is typed and produce any term in combinatory logic. So there's no guarantee, if you look at this, if you read this type as a specification, that the translation will actually preserve typing. So we're kind of not precise enough in our model just yet. So the obvious thing to do is to kind of account for simply typed combinatory logic terms. So just as we saw for the lambda calculus, we kind of record the variables that we're allowed to refer to, this capital gamma, a list of types, and the type of the overall term. So variables in application we've seen previously, they're kind of just the same as for the lambda calculus. But we have kind of 3 combinators, I, K, and S. And each of these, you can see, has a type which is easy enough. GHC can infer these types for you if you ask it. And now, if you look at the kind of translation type, it says, well, you take a well-typed term and you produce a term in combinatory logic, which has exactly the same type and the same variables in scope. So our goal is to define this translation function. How does that work? Well, there's 2 easy cases and 1 hard case. So we can map applications in the lambda calculus to applications in combinatory logic, and we can map variables in lambda calculus to variables in combinatory logic. If we have a lambda, we know we can recurse and kind of come up with a term for the body, but then we have to kind of somehow change the body a little bit and make it behave, find a combinatory lambda term which behaves like, combinatory logic term which behaves just like lambdas. And that's a function which is sometimes called bracket abstraction. So you're kind of introducing an abstraction or introducing a lambda, but you're mimicking that using combinators. It's a very standard translation. So if you can open a textbook, so this is Henk Barendrecht's lambda calculus, and you can go to definition 7.3.4, and you can see it defines a function, and the function is confusing me. It's usually called lambda star or lambda sub 1x, but it's a function. It's a function that manipulates combinatory logic terms. And if the term we need to kind of manipulate is x, the variable that was most recently bound, we introduce the combinator I. If it's a variable which is not x, or if it's a combinator like k and s, we simply write k of c. And if it's an application, we introduce an s combinator and recurse. So what does this look like in Agda? Well, you can see the 3 cases here as well. If we have to translate the most recently bound variable, we simply return I. In the other cases, we kind of introduce an extra k. And finally, for the case for application, we introduce an s and recurse. So this works, and all the types kind of go through. So I'm very happy that we have a kind of well-typed translation. We go from lambda terms to combinatory logic and preserve types. But now you can ask the next question, of course. Can you prove that this translation is correct somehow? So what would that mean, right? The first thing you have to think about a little bit is your specification. So one thing you might do is you might define a little evaluator for your kind of combinatory logic terms, saying that I'm now going to map a term in combinatory logic to, well, basically the same kind of semantics that I defined for the evaluator for the simply typed lambda calculus. I take an environment and I produce a value which lives in the semantics of sigma. So I know that I can map k into this lambda term, lambda xy to x, and I can map I into lambda xx. And the other cases kind of follow similarly. And now I need to prove one correctness statement, which says that if I have a lambda term t and I evaluate that, I might get a result out, or I can translate it to a combinatory logic term and do the evaluation there. And this really means you can mimic the reduction of any lambda term using combinatory logic. So this proof is mostly easy because it's just, structural induction. The cases for variables in application are not so hard. It's defined using an auxiliary function, so it's unsurprising that you need an extra lemma. And the extra lemma here basically reads that bracket abstraction behaves just like lambda abstraction. And once you have this lemma, the proof follows from immediate kind of induction, right? You do induction, you use induction hypothesis, you call this lemma, and you're done. So if the proof is so obvious, the next question you can ask is, can we make the entire translation correct by construction? And what would that mean? So you've already seen that the translate function guaranteed that it preserves types. Let's see if we can also make the translate function preserve semantics. So to do that, we kind of revisit the CL type that I had a few slides ago. And now you can see that it records a context, it records the type of the term, but it's also indexed, it takes an extra argument here, saying what is the intended semantics of the combinatory logic term. So you can see for the I combinator, for example, this is basically the right-hand side of eval CL for I. And this is just the right-hand side for eval CL of K, and similarly for app and variables, and S. So now the type of our translation function becomes something like this. So we take a well-typed lambda term, we produce a term in combinatory logic, which has the same type, but its semantics is going to be the result of evaluating T. Oh, okay, this seems like it might be very hard. But how do we define this function? It turns out that we don't need to change anything at all. The only thing that changes is the type. So we have this type for translate. It has exactly the same structure. The only thing which we need is that we need to redefine bracket abstraction again to also take into account that bracket abstraction behaves like lambda abstraction. But that's basically folding into the lemma that we proved in the original proof into the type of bracket abstraction. But the definition stays the same. If you look at Schoenfinkel's original papers, he had not 3 combinators, but 5 at least. So he had S, K, I, B, and C. And the idea behind B and C is that they're a little bit smarter. So what S does is it'll pass its third argument to both the first and the second. But oftentimes, you might be in the situation that the third argument is only used by the first or the second, but not both. So B and C are kind of special cases, and having these combinators can sometimes reduce the number of kind of reduction steps that you need to do in total. But to decide whether you want to use B, C, or S, you have to know something about kind of the free variables or how variables are used in your lambda terms. So could we redefine this translation to be a little bit smarter and use B and C instead of S whenever possible? So I can say a little bit about the kind of provenance of this paper. Namely, I wrote a correct by construction translation using B and C that was very smart. It used this code de Bruijn representation of variables, which I not only kept track of all the variables that were in scope, but also the variables that are actually used. And I could do something very clever, and it actually worked. And I submitted it to the journal, and then Ralph Hinze, who's the editor, he read the paper, he's very thorough, and he said, oh, I liked the first half, but the second half was much too complicated. And he said he gave a much simpler solution, so I'm very happy he did that. I think it really improved the paper. Because what he said is, well, why don't you just define a smart combinator, or a smart constructor, rather, for doing kind of the S application of 2 terms in combinatory logic. And if these terms start with an outermost k, it means it's throwing away their argument. And then that kind of gives you just enough information to tell whether you need to use B, C, K, or S whenever you build up applications. And it turns out you still don't need to do any proofs. So it's pretty amazing. So I should wrap up. And this seems like a parlor trick, right? Aren't I smart? I could manage to write a very complicated function with lots of lambdas and combinators, and it all went through like magic. But it's good to take a step back and think about what's the property that makes this work. And the translation we defined was very simple. It just used simple induction with one auxiliary function. And then when we tried to prove anything about this translation, the correctness proof was very simple. We used immediate induction, where we used our induction hypothesis, or we used an additional kind of lemma about exactly the auxiliary function. And if you have exactly the same structure in your proof and the same structure in your function, then the pattern matching is the same, the behavior is the same, then you can wrap them together, and it fits together perfectly. So it's whenever you see this kind of property hold, then that you realize that, oh, I could probably define this function in this correct by construction manner. Okay, that's all I had to say. Thanks very much.
We have time for questions.
Oh, yeah. Garrett.
Hi, Garrett Morris, University of Iowa. So the BCI calculus, of course, also captures linear lambda calculus. Have you considered whether you can do a correct by construction and translation of linear lambda calculus, and would that salvage your original Coe-de-Bruijn index approach when you no longer have K?
Possibly. So I tried something along these lines. So Oleg Kiselyov has this paper on semantic translation to combinators or something along these lines, where he uses a more linear system. So it makes where here kind of the cleverness is always in the lambda, basically, right? Because that's where you do the bracket abstraction. And his version is slightly different. It does more accounting for how variables are used, so that basically when the leaves are always I, because that's where you use the one variable that you have at your disposal, and then kind of the work is done in the application. And I found that if you try to do that in a kind of correct by construction fashion, the application definition was so clever, it did quite subtle pattern matching. It turns out that it was very hard to get the exact kind of behavior to go through that you wanted. So that might be one data point. I hope it's an answer.
Cool, thank you.
The standard chartered. So you have two typed languages, and you have two intrinsically typed representations for two languages, and then you're translating one to the other, and you had two separate evaluators for both languages. And then one of those two you put into the index of the type. So why that one, why not the other, or why not both? Like, does this asymmetry come from?
I think that's a fair question, because, well, mostly you're interested in the translation in one direction, because the translation from combinatory logic back to lambda calculus is much easier, right? Because you map variables to variables and applications to applications, and the base combinators all have a representation as a lambda term. So you could define that one as well, but it's...
But I'm not talking about like flipping the function. I'm saying that like, you only add the evaluator to the index of one.
Yeah. Right. So so your question would be, what would happen if you indexed the source language by its semantics and then define the translation directly? Oh, I think that's possible.
I mean, my question is not so much what would happen, but like, why is this the right way of doing?
Oh, okay. So this is the way it evolved, I would say. After polishing the Perl, I started off with this, and I thought, okay, let's see what happens when you define the conversion to combinators. And I realized, oh, I should write the proof, and then the proof is very easy. And then I realized, oh, I can actually fold this back in. But I don't think there's any reason you couldn't index the source language by its semantics and then have the translation like that, because it would be the same thing, basically. Yeah.
Okay, thanks.
Let's thank the speaker.
Oh, thank you.